Dear students, the next important topic in this electric potential is equipotential surfaces. This is an important question for the examination which you can expect for 2 marks. See, as the name itself suggests, a surface on which electric potential is same at all points, it is called as an equipotential surface. So this is the definition. A surface on which electric potential is the same at all points. This is called equipotential surface. To understand this equipotential surface, you consider a point charge here Q. So at a distance r from this point charge, the electric potential is given by 1 by 4 pi epsilon naught Q divided by R. So if I consider equidistant points from this charge like this, at this point, this point, this point, at this point, Q is same, R is same, at all points potential is same. Therefore, if I consider a line like this, a circle, along this circle electric potential is same, therefore this circle can be called as equipotential line. Instead of a circle, if you imagine a sphere, you imagine a sphere at the center of which this point charge is there, then at every point on the sphere electric potential is same, therefore that sphere can be called as an equipotential surface. Understand? So at the center of a sphere, if you consider a point charge, the surface of the sphere being equidistant from the center, every point on the sphere the potential is same, therefore the sphere can be considered to be an equipotential surface. Similarly, here there is a uniform electric field here in this direction. So along the direction of electric field, you learned that at different points electric potential is different. I told you that work done in bringing a unit positive charge from infinity to one point is different from infinity to some other point along the direction of electric field. Therefore, along the direction of electric field, electric potential is different at different points. So electric potential changes along the direction of electric field. If I consider a line perpendicular to this electric field, then the work done in moving a unit positive charge from infinity to every point on this line will be the same. That means electric potential every point on this line will be the same. Therefore, this line is called equipotential line. Instead of a line, if I consider a surface like this, perpendicular to the electric field, this surface can be called as equipotential surface. So, equipotential surfaces, they are perpendicular to electric field. Whether the field may be uniform like this or due to a point charge, here I told you that this is an equipotential surface, and due to the point charge electric field lines will be like this. So these electric field lines, they will be always perpendicular to equipotential surfaces. Here this is an equipotential surface, this is electric field, so this angle is 90 degrees. Here this is equipotential surface and this is electric field line, so here this angle is also 90 degrees. That means equipotential surfaces, they are always perpendicular to the direction of electric field lines. So these type of surfaces, they are called equipotential surfaces. On any equipotential surface, the potential difference is zero. Whatever potential is here, the same potential is also here. Potential being constant, potential difference is zero. When the potential difference is zero, the work done in moving a charge from one point to another point on an equipotential surface is zero. Because according to the definition which I told you in the last class, this work done is equal to this electric potential into charge. In the previous lecture, I told you about this point. W is equal to Q into V, where V is potential difference. On an equipotential surface, as there is no potential difference, no work is needed to be done in moving a charge on an equipotential surface. See, these are all characteristics of equipotential surfaces. You can also call them as properties. Properties of equipotential surfaces. The first one, they are perpendicular to electric field or electric field lines. Next, no work is done in moving a charge on equipotential surface. Based on this point, questions will be asked in the CET examination. Here there is a charge Q. What is the work done in moving another charge Q in a circular path around this charge? So obviously, this circular path will become equipotential line. So work done in moving this charge around this charge in a circular path is zero. So if you go through old question papers of CET examination, you will find these type of questions. So these questions are based on this point. Since W is equal to Q into V, as potential difference V is zero, this work done will become zero. The next thing is, here equipotential surfaces are perpendicular to field lines. In the properties of electric field lines, you learned that no two electric field lines intersect. When the electric field lines are not intersecting, these equipotential surfaces being perpendicular to electric field lines, no two equipotential surfaces can intersect. So they do not intersect. Equipotential surfaces, they never intersect. Next, any surface parallel to any equipotential surface is also equipotential. For example, this is the charge Q, this is an equipotential surface. If I consider another circle, this is also equipotential. Of course, there will be a potential difference from this surface to this surface. Potential difference can be there. But at all points here the potential is same. So this is one equipotential surface. This is another equipotential surface. Here also the potential is same. But there can be a potential, there will be a potential difference between here and here. So any surface which is parallel to an equipotential surface is also equipotential. Similarly, you take this case. There is a uniform electric field here. So according to this statement, equipotential surfaces are perpendicular to electric field. So this is equipotential surface, this is also equipotential surface, this is also equipotential surface. So all are parallel. Of course, there can be a potential difference from one equipotential surface to another equipotential surface. But on an equipotential surface, the potential will be same. So my point here is, any surface which is parallel to an equipotential surface is also equipotential. And further, in the properties of electric field lines, you learned that electric field lines are always perpendicular to surface of a charged conductor. Here this is a charged conductor. I told you that electric field lines are perpendicular to the surface of charged conductor like this. So field lines, they being perpendicular to surface of charged conductor, equipotential lines being perpendicular to electric field lines, you can say that the surface of any charged conductor is also an equipotential surface. So surface of a charged conductor is equipotential. So these are the some of the properties of equipotential surfaces. If this question is asked for 2 marks, you mention few of them. Next, in competitive examinations, you can also expect questions based on equipotential surface due to electric dipoles. Here there is a dipole. In this dipole, this is the direction of electric field, so this becomes the direction of equipotential surface. So, if you observe this equipotential surface around this point charge, then the surfaces will be like this. Similarly, for a system of like charges, Q and Q, there is a force of repulsion between them. So it will be like this. That means here the spacing is smaller, here the spacing is larger. In this case, the spacing is smaller, here the spacing is larger. So due to electric dipole, you will observe this type of equipotential surfaces, and for a system of like charges, you will observe this type of equipotential surfaces like this. They do not intersect. So this is all about the concept of equipotential surface. Next, by using this concept, we can obtain the relation between electric field and electric potential. Here we are going to obtain this equation, E is equal to minus dV by dr. This is an important derivation which will be asked for 3 marks in the board examination, and also based on this equation you can expect some questions in the JEE mains and as well as NEET examination. So this derivation is important for the board examination point of view. So the question will be asked like this: obtain the relation between electric field and electric potential, or prove that E is equal to minus dV by dr, or show that electric intensity is equal to negative potential gradient. The question can be asked different ways like this. Now we shall see how this equation can be obtained. Let us consider two equipotential surfaces. So this is one equipotential surface B, and this is another equipotential surface A. So this is A, this is B. The separation between them, these two equipotential surfaces, let this be dr, and the potential here is V, and here it is V minus dV, and this is the direction of electric field at P. So consider two equipotential surfaces A and B, separated by dr, having electric potential V and V minus dV or delta V, you can write. V minus dV or V minus delta V, both are one and the same. So V minus dV respectively. So here the potential is V, here the potential is V minus dV, and this is the direction of electric field. There is a potential difference of dV between these two. Now let us consider a point charge at P. So in moving this point charge from P to Q by dr, work is to be done. So let E be electric field at P on B. So here work done in moving +1 coulomb charge from P to Q against electric field dW is equal to, work done is equal to force into displacement. According to the definition of electric field, force acting on unit positive charge is equal to electric field. Therefore this work done can be written as E dr, E dot dr. So this is E dr cos 180 degree. So here this is the direction of electric field, this is the direction of displacement. So this angle here, it is 180 degree. This is equal to minus E dr. But this work done in moving a unit positive charge from P to Q against the electric field, this statement is nothing but potential difference. But dW is equal potential difference, that means V minus of V dV. So this is equal to dV. Therefore dV is equal to minus E dr. Therefore E is equal to minus dV divided by dr. E is equal to minus dV by dr. What this mean? Electric intensity at a point is negative of electric potential gradient. Negative of potential gradient. See, this dV by dr is nothing but change of potential with respect to distance. So change with respect to distance, it is called gradient. Electric intensity at a point is equal to negative of potential gradient at that particular point. So negative of electric potential gradient at that point. So this is the derivation which you need to do if this question is asked in the examination for 3 marks. First you consider two equipotential surfaces like this, and we considered the potentials to be V and V minus dV on these two equipotential surfaces. The electric field at this point is E. So work done in moving a unit positive charge from P to Q opposite to the direction of electric field, it is given by this equation. This work done in moving a charge from P to Q opposite direction of electric field is nothing but potential difference, dV. Therefore this potential difference becomes a dV, therefore E is equal to minus dV by dr. This negative sign signifies that the potential decreases along the direction of electric field. Electric potential decreases along the direction of electric field. So if I consider the electric field like this, in this direction, so along the direction of electric field the potential will decrease. Here the potential is higher, here it is lower, here it is still lower. Like that, along the direction of field electric potential decreases. That is what this negative sign signifies. The magnitude of electric field is given by dV by dr. Direction of electric field is given by this negative sign. So this is the relation between electric field and electric potential. From this expression you can make out these following points. The first thing is, since the magnitude of electric field is dV by dr, this unit of electric field is volt per meter. See, earlier in the previous chapter you learned that this E is equal to F divided by Q. From this equation you got this unit, Newton per Coulomb. So instead of Newton per Coulomb, sometimes the unit of electric field or electric intensity is also given as volt per meter. This unit has come from this consideration. So this is one thing you should remember. So overall, electric intensity unit can be written as volt per meter or Newton per Coulomb. Both are valid. The second point is, inside a charged spherical shell, this electric field is 0. So here there is a charged sphere of radius r. From the Gauss law, I proved that E is 0 inside the charged spherical shell. Since this E is equal to dV by dr, this dV by dr is equal to 0. That means V is constant. So, inside a charged spherical shell, electric field is 0 but not electric potential. Remember this point. See, as you know electric field is 0, you tend to write that electric potential is also 0, but not so. So inside a charged spherical shell, only the field is 0 but potential is not 0, potential is a constant. So electric potential inside the spherical shell, this one, it will be same as there on the surface. So therefore, the electric potential inside the charged spherical shell, it will be same as that on the surface of this charged shell, which is equal to 1 by 4 pi epsilon naught Q divided by R, where Q is the charge limit. So whatever potential is there on the surface, everywhere the inside the spherical shell, the same potential will be there. If I represent the variation of electric potential from the center of the spherical shell graphically, it will be like this. So this is distance R and this is potential V. So from the center up to a distance equal to radius, from the center up to a distance equal to radius, the potential is same. From here to here the potential is same. Outside the spherical shell, this potential varies inversely with the distance. So it varies like this. So V inversely proportional to R. So what is the difference between electric field and electric potential graphically? In case of electric field, from the center to the radius, field is 0. On the surface, field is maximum. So beyond this surface of the spherical shell, electric field varies inversely as the square of the distance, E proportional to 1 by R square. But in case of potential, from the center to surface, potential is constant. Beyond the surface, the potential varies inversely with distance. So you keep these things in mind. And further, with the distance, the potential varies like this and the field varies like this. So V inversely proportional to R, E inversely proportional to R square. You understand these graphs, and these type of graphical representations can be asked for 1 mark in annual examination. The next topic is potential energy. Of a system of charges. Potential energy of system of charges. While explaining electric potential, I told you that when a charge is in the electric field of another charge, it has got potential energy. Here there is one charge Q1. Due to this charge there is an electric field up to infinity. So in order to bring another charge from infinity to some point here, distance R. So in order to bring Q2 from infinity to R, work is needed to be done. That work done becomes equal to potential energy of this charge. So by definition, electric potential is equal to potential energy per unit charge. Therefore, potential energy is equal to electric potential into charge. With this idea, we can get expression for potential energy of system of charges. So first we shall consider a 2-particle system, and then we shall go for 3-particle system. For a 2-particle or 2-point charge, we shall say point charge. For a 2-point charges, for a system of 2-point charges, first we shall find the potential energy. Here there is a charge Q1 at O. So consider a charge Q1 at O in A. Due to this charge Q1 at this point P, distant R, what is the electric potential? Electric potential at P, distant R from Q1, is V is equal 1 by 4 pi epsilon Q1 divided by R. Next, let us bring another charge Q2 from infinity to R, like this. So, work done in bringing Q2 from infinity to R, that is potential energy, because work done is equal to potential energy. This U, or otherwise potential energy is equal to work done, that is V into Q2. Therefore, this U is equal to 1 by 4 pi epsilon naught Q1 divided by R into Q2. Therefore, U is equal to K, 1 by 4 pi epsilon Q1 Q2 divided by R. This is the expression for potential energy of a system of 2-point charges Q1 Q2 separated by distance R. So this derivation is very simple. First I considered a charge here. Due to this charge at this point, this much of potential is there. In order to bring another charge from infinity to this point, work done is given by this potential into charge. So here the potential is V and charge is Q2, which is brought from infinity to P. Therefore, this work done being equal to potential energy, the potential energy of a system of 2-point charges Q1 Q2 separated by distance R is given by this expression. In a similar way, you can also find for a system of 3-point charges. Here we shall consider 3-point charges Q1, Q2, Q3 kept at A, B and C at 3 points. So this distance from A to B be R1, B to C, let this be R2, C to A, let this be R3. So, let a system of 3-point charges are kept like this. We have to find the potential energy of the system. So, potential energy is nothing but work done in bringing the 3 charges together like this. First, when these 2 charges are there, the potential energy or work done. Work done in bringing Q1 and Q2. Separated by R1. So this is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R1. See, when a system of two charges is to be formed like this is the work done, so this becomes the potential energy. So due to these two charges there is electric field here. There will be electric potential here. In order to bring the Q3 from infinity to C, work is done. That work done is nothing but potential into this charge. So first we shall find the potential at C due to Q1 as well as Q2. So electric potential at C due to Q1 and Q2, V is equal 1 by 4 pi epsilon naught Q1 by R1 plus 1 by 4 pi epsilon naught Q2 divided by R2. Due to this charge at this point, this is the potential. Due to this charge at this point, due to Q1 at this point C, due to Q1 at the point C, potential is 1 by 4 pi epsilon naught Q1 by R3. Due to this charge Q2 at this point C, the potential is 1 by 4 pi epsilon naught Q2 divided by R2. Therefore, work done in bringing Q3 from infinity to C So this is this potential V into Q3 plus this potential V into Q3. So this U2 is equal to, so work done in bringing Q3 from infinity to C. So this potential into charge, therefore 1 by 4 pi epsilon naught Q1 Q2 divided by R3 plus 1 by 4 pi epsilon naught Q2 divided by R2 into Q3. So this is the work done in bringing Q3 from infinity to C. This is the work done in bringing Q2 from infinity to B. Therefore, total work done in forming the system of three charges. Therefore, total work done or potential energy of three charge system. This U is equal to U1 plus U. So if I add these two terms, this U is equal to 1 by 4 pi epsilon naught. This is Q1 Q2 divided by R1. And here 1 by 4 pi epsilon naught Q2 Q3 divided by R2. Similarly, this term 1 by 4 pi epsilon naught Q1 Q3 into R3. So this is the expression for potential energy of a system of 3-point charges. So first, for these two charges, this is the potential energy. When the third charge is to be brought into the electric field of these two charges, what is to be done? against the electric field due to Q1 and also against the electric field due to Q2. So work done in bringing Q3 against electric fields due to these two charges is equal to electric potential at this point due to these two charges into this charge. Electric potential at this point due to these two charges into this charge. So electric potential at C due to Q1 and Q2 is this one. So work done in bringing Q3 from infinity to C is this potential into charge. So total work done in forming the system of three charges is given by sum of these two works. Therefore, I added these equations, you get this term. So this is the electric potential of a system of three charges. From this expression, if all charges are same, if Q1 is equal to Q2 is equal to Q3 is equal to Q, and all distances are equal, then all these three terms will become same. Then this expression will become 1 by 4 pi epsilon naught 3q square divided by r. That means when three identical charges are kept at the corners of an equilateral triangle having side r, then this becomes the expression for potential energy. So here, if you observe this equation, it is nothing but when three charges are there, total potential energy is nothing but sum of potential energies of system of pair of charges. That means potential energy of these two charges plus potential energy of these two charges plus potential energy of these two charges. Sum of these terms will give you total potential energy. Similarly, if I consider four charges, Q1, Q2, Q3, Q4 like this. If you apply the same logic as this one, then the potential energy of system of four charges is given by potential energy of these two plus 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 potential energy of these two. That means how many terms will be there then? 1, 2, 3, 4, 5, 6 terms will be there. So in general, number of terms in a system of n charges, it is given by n into n minus 1 divided by 2. When only two charges are there, then there will be only one term like this. When three charges are there, 3 minus 1, 2, so 3 terms will be there like this. When four charges are there, then 4 into 3 divided by 2, 6 terms are there as I told you here. So in general, the number of terms in a system of n charges is given by this equation. So the simplest way of finding the potential energy of system of charges is every time you consider two charges, you find the potential energy and you add all the terms. So this is the potential energy of charges in the absence of electric field. Here I did not consider any external electric field. These charges are present in the electric field of one another. Suppose in addition to electric field due to one another, there is also an external electric field like this. Then how to get the potential energy? That we shall take it in the next class.